Okay, good morning, everyone, and welcome to the CSR Group seminar and research talks. We will begin with a brief presentation about the group by the group head, Professor Nananathan. And after that, we will be playing a pre-recording, 3-minute pre-recording presentations of the research. Okay, so let's start off with Professor Nananathan giving us a few minutes briefing about the research group. All right.
Okay, thanks, Majid. So I can share the screen. Okay. So can you see my screen?
Yes.
Okay. Okay, good morning, everyone. So I'm Nananathan, the head of the group. So this group started in 2017. So actually 3 years back. So in the group now there are 9 faculty members, 2 full professors, 1 reader, 2 senior lecturers, 4 lecturers. So PhD students and postdoc total around 25 plus. So our research funding mainly from, we have had 4 or 5 EPSRC grants on 5G, then Innovate UK. Recently we got 2 industrial grants from Huawei. So one is on NOMA, other one is on artificial intelligence for beyond 5G. So the group research output is significant. Over the past 3 years, we have had around 150 top journal papers, 70 top conference papers, and we received 2 best paper awards. So our research activities for the past several years, mainly on 5G. So in 5G, so the different aspects, so that means on 3 pillars: enhanced mobile broadband, massive IoT, and critical IoT or ultra reliable low latency communications. So in enhanced mobile broadband, we have been working on millimeter wave communications, massive MIMO, full duplex, and so the high spectral efficiency techniques. Also, we have been working on cell densification, ultra dense small cell network. So we have done numerous works on critical IoT as well as massive IoT. So massive IoT modeling and the application of artificial intelligence in massive IoT, critical IoT, so for industrial applications, so ultra reliable low latency communications. So our current research activities are for beyond 5G research. So beyond 5G research, so mainly so the fusion of the virtual and the physical systems. So our research mainly focused on artificial intelligence enabled wireless communication. So that means so AI in unmanned air vehicles, artificial intelligence in UAV. So we have been working on artificial intelligence in massive IoT, artificial intelligence in to enhance the throughput as well as coverage. So we have been working on the emerging areas, say like intelligent reflecting surface and other new areas. So that means our research focus mainly towards the 6G. So for further details, you can find from the homepage of the group. Thank you. So have a nice webinar. So next 1 hour. Thank you.
Okay, great. Thank you, Nananathan. We'll start off with the first talk. I'll share my screen. All right. And the first talk here.
Hello and welcome.
Okay. The title of the talk is A Novel Channel Model for Reconfigurable Intelligent Surface Assisted Wireless Networks. Okay, let's begin. So the name of the speaker is Jackie Zhu, and this is the email. Okay, so if you find the topic interesting, you would like to, if you have questions and you would like to interact and take this further, you can always email the presenter. Thank you.
I'm Jackie from the CSR Group. In this video demo, I'm going to present the recent research work by Dr. Yuan Wei and me entitled A Novel Channel Model for Reconfigurable Intelligent Surface Assisted Wireless Networks. The RIS, which is short for the
Majid, we can hear only the voice, not the screen.
technology
Slide.
to enable a smart radio environment in the new.
Let me see why that is.
Hello and welcome. I'm Jiaqi from the CSR Group. In this video demo, I'm going to present the recent research work by Dr. Yuan Wei and me in.
So no, just the voice.
The only voice is coming. Earlier, it was okay.
Oh,
You follow the same procedure.
I did. Let me see. Let me see like this, maybe.
Yeah, now it's fine.
All right, okay, good. So the title of the talk is A Novel Channel Model for Reconfigurable Intelligent Surface Assisted Wireless Networks. Okay, so this is the name of the speaker and also the contact and the email in case you would like to keep in touch. Thank you.
I'm Jiaqi from the CSR Group. In this video demo, I'm going to present the recent research work by Dr. Yuan Wei and me entitled A Novel Channel Model for Reconfigurable Intelligent Surface Assisted Wireless Networks. The RIS, which is short for the Reconfigurable Intelligent Surface, is a promising technology to enable a smart radio environment in the near future. In traditional wireless networks, the electromagnetic wave response of the scattering environment exhibits a random nature. This is because the phases of the multipath components are random. By introducing the RIS, the signal reflected on the RIS has controllable phase and even amplitude. In other words, theta m can be programmed to take on specific values, or at least fall into a desired angle range. Thus, the strength of the received signal at the terminal can be enhanced. How to reflect this unique characteristic of the RIS in channel modeling become a question. As a result, we present this work to facilitate the research of modeling the RIS-assisted channel and to draw more attention on how to incorporate fundamental electromagnetic theories, such as the general law of refraction and reflection, as well as the physical parameters, such as the quantization level, into existing wireless communication frameworks. The existing research adopt a channel modeling method which we refer to as the separate model. In this approach, the link through the scattering environments and the links through each RIS element are separately studied. This model is applicable to general scenarios. However, the distribution of the overall channel, which can be expressed as this, is usually hard to obtain in closed form. We represent our joint channel to compactly express the overall channel distribution and to show how important RIS physical parameters affect the channel. Here I would like to show some of our simulation results. On the left-hand side, we illustrate how well the joint channel fits into the distribution as we predicted. It can be observed that the analytical prediction fits well with the simulation results. On the right-hand side, we also did some simulations about the outage probability. The details of those simulations can be found in our paper uploaded to arXiv. This is the end of the video presentation. Thanks for watching and have a great day.
All right, everyone. So this was the first talk. Again, this is the name of the speaker and the email. Please jot this down for further cooperation. Okay, so the next talk. All right, so again, the name of the talk a cellular network offloading with intelligent UAVs. Okay, so UAVs is a topic that the group works on, and we have a lot of students and collaborators working on this topic. So UAV is a very popular topic within the group. Again, the name of the speaker and the email is there for you in case you would like to stay in touch. Thank you.
Hello everyone, I'm Reconfigurable from CSR Group. Today, the topic of my presentation is cellular network offloading with intelligent UAV. I believe everyone has suffered from these situations that in your lives, your cell phone lost connections or only has disappointing data rate. For example, when you are on a crowded road or a shopping mall, the ground-based station may be overloaded due to the large user number, and it cannot provide proper service for you. Another typical reason for the connection loss is that the users may be too far away from the base station, or the propagation path may be blocked by buildings. Therefore, to rescue these poor users who suffered from this situation, we can employ a UAV fleet to provide internet service to these users who cannot obtain qualified services from the conventional ground-based stations. Such as shown in this figure, these two users are blocked by this building, so they would be offloaded to the nearby UAVs. Our framework has following superiority compared with the cellular network. We have the mobility and the flexibility, and then our UAV has better channel quality compared with ground-based stations. At last, we invoke the NOMA technique to improve the user fairness. However, a real problem is how to decide the trajectory and other actions of the UAV. We employ the deep queue network as a brain of the UAV. We allow the UAV to make attempts to take some actions, and they can receive the reward and get to the next state. We keep doing this circle, and we call it training. After a sufficient training episodes, the UAV are able to know which is the best or the optimal action. In this way, we build our smart UAV to service the general public. And from this figure, we can see how much the data rate of users are improved by our machine learning algorithm. That's all. Thank you for your listening.
All right, perfect. And obviously that was the speaker with a mask. Okay, the name of the speaker and the email is there for you to get in touch. Okay, thank you. Okay, third talk.
Hello, everyone. My name is.
Okay, so IRS, once again, it's a very popular topic for the group. We have a lot of students and postdocs working on this. The name of the speaker is there for you to get in touch along with the email. All right, so if the topic is of interest, please get in touch. Thank you.
In this presentation, I'll introduce my recent work, which has been published in IEEE Transactions on Signal Processing. It is robust performing in intelligent reflecting surface aided communication systems. An IRS is a thin surface made of nearly passive antennas, which are capable of modifying the incident signals so as to enhance the spectral efficiency and energy efficiency. It has the advantage of low circuit complexity, low power consumption, and flexible deployment. However, due to the lack of RF trims at the IRS, the perfect channel state information is impossible to be obtained in practice. So it is impossible to investigate the robust performing in the IRS systems to deal with the channel uncertainty. As we can see, delta is the error channel. In this work, we adapted two channel error models to characterize the channel error. The one is the bounded CSR error model. Based on this, we design a worst-case robust performing. Another one is the statistical CSR error model. Based on this, we design an outage-constrained robust performing. If you are interested in the details of problem formulation and algorithms, we would like to invite you to read our paper. The left figure illustrated the achievable transmit power versus the target rate. We come to the conclusion that the outage-constrained performing outperforms the worst-case performing due to the fact that the worst-case optimization is the most conservative robust design, and due to its nature, it is suboptimal when the worst cases happen with small probability. The right figure shows the impact of the IRS size and the channel error on the performance. As we can see, increasing the number of reflection elements cannot only reduce the transmit power due to its increased performing gain, but also increase the channel estimation error that more transmit power is required to compensate for the channel errors. So the final transmit power decreases at low channel error and increases when the channel error is over 0.1. As a result, the IRS size should be carefully chosen, and the accuracy of the channel estimation is crucial to use the benefits offered by the IRS. Thank you for listening.
Okay, great. Once again, this is the name of the speaker and the email, and please keep in touch. As you saw, we had 3 talks, and these talks covered the topics of UAV, IRS, NOMA, and AI. Okay, so once again, these are the main topics or emerging technologies that we work on. Okay, so let's go on to 4th talk.
Hello, my name is Yasmin, and I'm going to...
And as you can see, it's on IRS. So it's IRS-aided communication systems with imperfect channel acquisition, right? So the name of the speaker and also the email. Okay, so keep in touch. We'll begin.
Talk about IRS-aided communication systems with imperfect channel acquisition. The system I'm going to consider is IRS-aided NOMA. At first, I'm going to do the introduction, then go through the methodologies and numerical results, and finally talk about the future contributions we might have to this project. NOMA, or non-orthogonal multiple access, is when we serve multiple users on the same orthogonal resource block, and it has high spectral efficiency. OMA, on the other hand, is when we dedicate each resource block to only one user. It has 3 kinds: TDMA, FDMA, and SDMA. It might seem that NOMA is always better than OMA, but it is not the case. For example, NOMA is only better than SDMA in case the direction of users' channel vectors are similar. To broaden the application of NOMA, we have to manipulate the direction of users' channel vectors, and that is why we use IRS. This method has been previously considered in the literature, but as far as we know, no one has ever considered the effect of channel estimation error in their system model, and that is what we're going to do. So, what is intelligent reflecting surface? An IRS is a planar array consisting of large number of passive phase shifters, and we use it to reconfigure the propagation environment. It is low-cost, lightweighted, easily implantable, and power efficient. The system we're going to use has 2 users, and one is near user and one is far user. We're going to use NOMA here, and we're going to use an IRS to reconfigure the propagation environment. To formulate the problem, we need to first calculate the rates of each user, provided the fact that we're using NOMA in the system, and then formulate an optimization problem to maximize the sum rate. As you can see here, this optimization problem has too many variables and we need to decouple those variables. That's why we use penalty dual decomposition method in order to decouple the optimization variables, and finally we are able to design an algorithm in each step of which we can calculate each variable separately by a closed form solution. And the fact that the solutions are closed form means that it has very low computational complexity. And as far as the performance of the method, we can see that the robust algorithm is it has a performance near the perfect CSI design. So in the future, we are going to provide comparison between the robust IRS-aided NOMA with its OMA counterparts, FDMA, TDMA, and SDMA. Thank you for your time and attention. Goodbye.
Okay, great. Okay, so name of the presenter and the email. Thank you. Let's move on.
Hello, I welcome you all in today's session. My name is...
Okay, so this is the fifth presenter and the email. Right?
and I am presenting reinforcement learning for user clustering problem in NOMA-enabled uplink IoT. Before proceeding towards my presentation, I would like to thank my university and my supervisor to provide such a diverse research environment. Here's the outline for my presentation and targeted, that also represent the targeted research area in the proposed figure, in the presented figure. So our research problem is in wireless systems to improve the user clustering or resource allocation in NOMA-enabled uplink IoT. What is NOMA? Traditional systems or previous networks are OMA-based. OMA means orthogonal multiple access that allows one user for each subchannel or resource block or cluster. And in NOMA, we can serve more than two or more than two users. So we use artificial intelligence to improve or to address this issue. Why artificial intelligence? First motivation is that this problem is non-convex problem. So traditional models are failed to solve these kind of problems. Secondly, these are model-free algorithms. So you can design any kind of system that can provide a long-term generalized solution, learning-based solution, to handle multiple constraints efficiently. So reinforcement learning is basically based on three elements: state, action, and reward. So we are using these elements to optimize the resource allocation problem in wireless systems. As we can see, the framework in the figure provided. So using reinforcement learning, we optimize the clustering problem that is also considered as sub-channel allocation or resource allocation problem. So in our system, each sub-channel represents one cluster. Therefore, we try to serve more than two users and optimize for each cluster or resource block based on artificial intelligence algorithms. And we choose DQN, deep Q networks or deep Q learning and SARSA algorithm to solve this issue in multi-cell environment. Here are the outcomes. From these figures, we can see that the figure highlighted in blue is for convergence, and the figure highlighted in green is the long-term system utility, and short-term system utility is presented in a figure that is highlighted in red. So the first figure that is highlighted in blue shows the convergence of DQN that is very fast because of the power of neural networks. and SARSA is on the second number even. For the DQN, the number of user equipments, UE, are more than SARSA. The simultaneous connections, these represent simultaneous connections are 10. That is more than SARSA, because for SARSA, we are just using 3 simultaneous connections for each resource block. So as you can see, the power of DQN is convergence here. So for long term, we can see that DQN also provides better resource allocation than OMA and then SARSA. SARSA is on second number in terms of resource allocation. And for the third figure that is highlighted in red, we can see the short-term trends for both of the algorithms versus different bandwidth and learning rates. So that's all. Thank you for your time.
Okay, great. And this is the name of the presenter and the email. Okay. 6.
Hello everyone, this is Xiaoliu from CSR Group. I'm supervised by Professor Yue Chen, Dr. Yuanwei Liu, and Dr. Michael Chai. It's my great honor to have this chance to present our research contributions on artificial intelligence-empowered UAV communication networks. Nowadays, UAVs are playing an important role in 5G wireless networks and smart city. Owing to their agility as well as their ability to establish line-of-sight wireless links, UAVs can be used as aerial base stations to complement the existing terrestrial communication networks. Because they can be flexibly redeployed in temporary teletraffic hotspots, they can also replace cellular networks to provide emergency wireless services after natural disasters. In addition, UAVs can be also invoked as intelligent aerial users for supporting autonomous services. In our work, we mainly focus on invoking UAVs as aerial base stations because UAVs are expected to provide uninterrupted and ubiquitous connectivity for devices in the future smart city. In contrast to the existing research contributions, the main contributions of our work are to answer the questions including why do we need artificial intelligence? What are the key features of artificial intelligence-enabled UAV networks? What kind of machine learning algorithms are suitable for designing UAV networks, as well as how big data tools and machine learning algorithms cope with the dynamic environment and improve the performance of UAV-aided wireless networks. In terms of the objective functions, we mainly focus on optimal 3D deployment placement of UAVs, energy efficiency design, and the trajectory design of UAVs, resource allocation and interference management of UAV-aided wireless networks. If you are interested in this topic, please refer to our published papers. Thank you very much.
Okay, great. Once again, this is the name of the presenter and the email. Okay, we'll go on to the 7th talk.
Hello everyone, today I will present the work about analyzing grant-free access for URLC service.
Okay, I just wanted to also give you the email of the presenter. Okay, so yan.liu@qmul.ac.uk.
We know that the 3GPP has defined a general URLC requirement shown in the table, especially the low latency and the high reliability requirements. In our work, we defined the URLC quality of service in equation 9, considering both the latency and the reliability requirements. Recently, grant-free access has been proposed to cope with the UIRC requirements. With uplink grant-free access, a user can transmit data along with requirement to control information itself. This can greatly reduce the latency by removing the scheduling process in the grant-based transmission as shown in Figure 1. In this work, we proposed 3 grant-free schemes and presented a novel spatial temporal mathematical framework to analyze and evaluate the reliability and latency performances for 3 schemes, including the reactive, the K-repetition, and the proactive schemes. As shown in Figure 3, in the K-repetition scheme, predefined number of the same packet are transmitted without waiting for the feedback, and then the base station performs soft combine of these repetitions to improve the reliability. When the repetition number K equals to 1, it refers to the reactive scheme. As shown in Figure 4, in the proactive scheme, the user still repeats transmissions in consecutive slots like the K-repetition scheme, but if the user receives a positive feedback from the base station before reaching the maximum repetition value, the repetition will be terminated to reduce latency. In our simulation results, we can see that both the K-repetition and the proactive schemes can provide a lower latent access value probability. The proactive scheme can provide the lowest latent access value probability under shorter latency constraints, and the K-repetition scheme can provide the lowest latent access value probability under longer latency constraints, but depends on the K value. That's all for my presentation. Thanks for all your time.
Okay, great. The name of the presenter and the email. Okay, let's move on to the 8th talk.
Hello, and thank you for attending this talk. My name is Mona Jaber, and today I will be talking about...
I'll just pause this to provide you with the email of the presenter. Right.
Spectrum sharing in a heterogeneous network, which is made out of small cells and macro cells. And the spectrum sharing is between the backhaul axis and the radio axis. The first question you may ask is, why do we need small cells and why do we need a wireless backhaul? Well, small cells are a perfect solution to cater for the demand and throughput of today's networks and users. However, these small cells need to be connected to the network through a backhaul link. The ideal backhaul link will be a fiber optic based solution. However, fiber optic is not available everywhere and is very expensive to deploy. For that reason, wireless backhauls are used as a fast and cost-effective solution. Why do we need to use in-band backhaul? Well, the radio spectrum is already finite and crowded, so we need to make the best out of the spectrum that we have. And for that reason, we propose to use in-band wireless backhaul, which means that the same spectrum is used for both the radio axis and the backhaul axis. And we posit that the diversity that we have in today's networks and more diversity to come with the Internet of Everything will be a place that we can exploit in order to optimize the usage of the spectrum. How do we do that? We propose to use distributed reinforcement learning, which is a machine learning approach that learns from the data that it receives. The problem statement that we have is that I've got a fixed spectrum and I want to know how to best use that spectrum to serve the radio axis of the macro cell, the radio axis of the small cell, but also the backhaul of the small cell. Traditionally, the spectrum is split into two portions, one which is allocated to the radio axis and the other one to the wireless backhaul. We posit that this is not the optimum way and we should be optimizing where that line is drawn according to the traffic demand. And this is what we call the question 1, where we optimize the value of eta. We go further and we want to optimize for each one of the small cells how that N-band wireless backhaul is used. And we want to posit that some of that spectrum can be reused for radio access just for that small cell. And this is where we go and optimize eta-S for each one of these small cells. And I'd like to show some of the results. So in order to do that, I look at the network-centric and the user-centric results. In terms of network-centric, if I optimize eta, I can achieve 23% gain compared to the fixed split. And if I optimize eta-S further, I can improve the gain by 3.5% extra throughput from a network-centric perspective. If I look at the user-centric perspective, then compared to the fixed split, I can get up to 58% extra throughput as perceived by users and 15% better latency as perceived by users. If I go further and optimize my eta-S, then I can have 12% better throughput and 5% lower latency for my users. So these results are very encouraging, and the takeaway message is that networks are becoming indeed more complex, but also more diverse, and diversity is a gain, especially if I can adjust the elasticity of the network to match the diversity and generate the gain. For that, we propose to use data-driven machine learning approaches. Thank you very much for listening, and if you have any questions, I'll be very happy to answer that.
All right. Okay, so the name of the speaker and the email. And now this will be our last and final talk. The name of the speaker and the email is provided for you, right? And let's begin.
Dear teachers, I'm going to share my presentation about a wireless vision dataset for pervasive preserving humanity recognition. We developed 4 parts. First is background motivation. Humanity recognition important as in numerous applications as assisted living has more generally centric. Existing active monitor system require individuals to wear a device which is not convenient. But in passive monitor system, camera-based sensing methods are limited by occlusion problems and refer to privacy issues. Wireless sensing is not intrusive without privacy issue and is sensitive to light conditions. So it's very convenient for us to propose a Wi-Fi-based and video-based neural network for activity recognition with synchronized video surveillance deployment for the various data. We're using camera to gather videos. We divide the videos into the frames and put it into the AlphaPose existing state-of-art neural network as a vision channel to gather coefficient maps. Then we're using the various data to train ResNet as a Wi-Fi channel, and the coefficient maps is used as the supervisory signals for ResNet training. We got the coefficient maps and extract the human skeleton from the coefficient maps. Its whole structure is WNN. Then we're using the sport vector machine as a Wi-Fi channel for action classification, and also human skeletons using the sport vector machine for action classification as a comparison. Then using a traditional convolutional neural network short for CNN as a Wi-Fi channel for action classification. We must know the basic knowledge about the channel state information, which is used as a wireless data in our work. We also collected the wireless vision dataset is known as WiVi. The whole floor plan is shown above the figure, and the transmitter desktop and the receiver dashboard are fixed located on the left side of the office, and the volunteer persons perform activity in different areas to simulate the occlusion cases. And various data and vision data are simultaneously synchronously collected. To simulate as many situations possible, 3 scenarios has been designed. This is including the scenes without inclusion, partially occlusion, and full occlusion. This is scene without any occlusion. The person female perform falling down, and perform pushing, and perform cage kicking, and another person performs throwing. And this is partial occlusion, the male performing sitting. Another person performs falling down. EECS proposed a Wi-Fi scheme, proposed a Wi-Fi-based and video-based neural network as WIN for activity recognition, also collect the Wi-Fi dataset for as a benchmark. An experiment shows the Wi-Fi dataset satisfied primary demand, and the WIN achieved most robust results. Future, we will extend the diversity of the dataset and investigate the more robust deep learning pipeline to realize automatic selection input. Thank you.